Yes, sir.
Okay, good. Can you see my screen?
Yes.
Oh, good. So let's begin. So in the last class, we have talked about this particular architecture where we have seen that in VG16 we have a couple of convolution layers followed by what do we have here? Followed by this max pooling layer. At the end, we have this fully connected network connection. And then finally, we have this soft network. Okay? And this kind of architecture, we have seen that there is a lot of parameters that we have to train. Okay. Though in this network there is a simplicity in train. That is, each time we do this convolution called the max pooling, the dimension is halved and the depth is increased. That means as you move forward through this number of forward layers, what will happen? The number of filters is increasing by with 64 filters, then 128 filters, then 256, then 512. So every time the number of filters is basically increased by 2. And if you look at the height and width, the size has been halved in each block of convolution layers. Okay. Now we'll be talking about a different kind of network that is known as the ResNet. Okay. So what we see here with the problem of deep neural networks as we have more and more layers. Okay. Let's say if you start from this input and you have more and more layers, going after one after another, like this. You're going through like this. Okay. So we know that once we compute this output y hat, okay, so we compute the loss function, then we compute the DL, DW, and then we use this. Okay, let me plus for the time being. Okay, we use this to update the value of W, right? Now, how did we compute this DLW? Because even for, let's say for this particular weight over here, okay, let's say we have a weight for let's say for layer 1. Even for this layer, we have to compute the derivative with respect to DL, DW. And we know that using this chain rule of calculus, okay, we have seen that we have some terms, okay, and this goes like this. I mean, some terms like that, okay, DW1, okay. This chain rule we are computing to compute this update factor, okay. But the problem is that since the network has gone deeper and deeper, okay, what will happen? These derivative terms, okay, these derivative terms, if they are small, so a lot of small derivatives will be multiplied here and there, then as a whole, this update factor will be very small. Then this is called this vanishing gradient problem. That is, the derivative you're computing is going to be close to 0. It can happen the other way around. If the derivative values are larger, so if the large values are multiplied with each other, what will happen? The update term will be very large. And if it is very large, what will happen? The problem is that it is going to be very hard to train the network. For example, in the simplest case, if we have this vanishing gradient problem, if this whole term becomes close to 0, do we have any change with W's then? Yes or no? Can you hear me?
No, sir.
You cannot hear me, or there will be no change? Which one did you answer?
No change.
No change. Okay. So this is basically a problem of vanishing gradient problem. There is another kind of problem which is the exploding gradient. That means if the value of this value is very large, okay, if this is very large, okay, what will happen? The value of W, which has been updated, will be significantly large. And if it is significantly large, even you will see that the network, okay, it cannot train well, it cannot learn well. Okay, so that means you will see that the training error will start to increase. Okay, so this is going to be the problem you will be facing. So how to take care of that? What say this is what this ResNet or residual network, this is also known as residual network, is going to solve it. Is going to introduce this skip connection. You can see this skip connection over here. That means whatever the input you have here, this input, that means this is the output, though I can say like this is the output from the previous layer, or this is basically your input. So this is going to be added up with the input of one of the further subsequent nodes or subsequent layers. Okay, so how does it normally work? If I did not have this skip connection, what would have happened? Okay, so how do we compute this activation of L+2 layer? The activation is that you simply compute this sigmoid function, okay, this activation function
on the input here. Okay, if I want to see the input here, what is the total input? The total input is basically the input to this layer, this L2 layer, right? And if you consider the bias too, so this is what we have. So this is the basic thing that we have seen earlier, right? Yes or no? And how did you compute this, the value of Z? The value of Z was computed by multiplying the weight of layer 2, okay, multiplied by which one? Multiplied by the input coming to this layer L+2. What is the output from layer L+1? That is activation of L+1. That is being that is acting as the input for the next layer. So this is the activation of the previous layer, but now it is the input of the next layer. And of course, if you consider the bias, so this is what we have. Okay, this is what we have. Up to this, is it clear? This is a basic calculation that we have seen earlier. Nothing new over here. Okay, so now you can see that the additional terms that we have incorporated here. Now, if you look at the skip connection, okay, if I put the red. So now if I include this skip connection, what will happen? What is coming to? The activation that came from the even 2 layers before, that is from layer L. That is what we have added over here. So that means even if, let's say, for the time being, if you just forget about this bias term, okay, even if this term, okay, even if this term becomes 0 or it has no effect, okay, let me say like this, it has no effect. And if it has no effect on this activation function, what will happen? What can take the control? Which one can take control? This one can take control for computing the output of this activation. Is this clear? Yes or no? What happened? In this class, we have near about like 50 students. Nobody is responding. Hello, can you hear me?
Yes.
So this is basically the motivation behind this residual network. That means we'll have residual connection, okay, one after another, okay. So now we will see the benefit of using this residual connection. So if we did not have any residual connection, that means if it was a plain neural network, okay, and we can see that as we increase the number of layers, okay, the more and more layers that we are having, normally what happens, the training error decreases because we can extract more and more features. But if we have too many layers, the problem is that once we have this exploding or vanishing gradient problem, we see that, okay, fine, the error will start to increase. Okay, but this does not happen, okay, if we include this residual connection of, among the layers. Okay, what will happen? It will allow us to increase even more the error with more and more number of layers. Okay, is this understood?
Yes, sir.
Okay.
Yes, sir.
The next one we'll be talking about is this one-by-one convolution. In case of one-by-one convolution, what we do, okay. So let's say if the input is 28 by 28 into 192. So if I define a 1/1 into 192 filter, so this filter will be something like that, right? Yes or no? Okay, so this filter is 1 into 1 into 192. So if I apply this 1 into 1 by 192 filter on this one, so if I place it over here, so for this single position, basically it will be covering all those elements in that particular direction, right? Okay. So if I do that, what will be the output value? The output value is going to be a single value. So if I do it for all the input of 28 into 28 into 92, what will happen? The output will be of size what? Output will be of size 28 by 28. This is what will happen for a single filter. Now, if I use 32 different filters, what will happen? You will have 32 different outputs of size 28 into 28. And if I stack them together, okay, what will happen? Your total output size will be 28 into 28 into 32. Now, if we do the same convolution, okay, for the time being, we have done this same convolution, and it doesn't matter whether it is same and valid because we have a 1/1 filter. Okay, you don't need any padding. Okay, Now, what was the difference here? The difference was previously the depth value, the channel number was 192. We have reduced it to what? Only 32. Can you see it? Yes or no?
Yes, sir.
Okay. Because normally whenever we are doing this max pooling, the max pooling shrinks what? Shrinks the height and width of the input, right? But if we do this one by one convolution, the benefit is that basically we can reduce the number of channels. Okay, this is the main motivation of using the number of channels. Also, it will help us to reduce the computational cost in successive operations. We'll see how. Okay. Now we'll talk about this inception network. So this inception network will use the concept of one by one convolution. But before talking about that one, the motivation behind the design of inception network is that, let's say, what we have done in different convolution layers, you have picked 3 by 3 filter, or maybe you have picked 5 by 5 filter. Okay. So someone asked me in the previous class that how do we choose the filter size, whether it should be 3 by 3, 5 by 5, 7 by 7, or whether it should be a max pool layer instead of a convolution layer. Okay. How do we pick it? Okay. So for this thing, what we'll do, inception network, okay, it will basically what it will do, it will let us to decide, okay, which filter to use in which particular layer. Is this understood?
Yes, sir.
That means we want to automatically select whether I should go for 3 by 3, or whether I should go 5 by 5, or whether I should have a max pool layer, or whether I should take a 1 by 1 convolution. And if you train your network, it will know that in which block, whether it will pick this one, or it will pick that one, or maybe it will pick that one. The network will decide it for during the training stage. Okay. So
Yes, sir.
normally what we'll do in this particular case, first of all, since at the very beginning, we don't know which one will perform better. So what we'll do, assume that for this particular input, if I apply this one by one convolution filter, and I have taken, for example, if I have taken 64 filters of one by one filter, then your output size will be of what size? What will be your output size?
28 into 64.
Yeah, it's going to be 28 into 28 into 64, right? Now,
Yes,
if
sir.
I do 3 by 3, same convolution, and I have picked 128 filters. So what will be the output size? It's going to be 28 into 28 into what?
128.
128. Then if I take a 5 by 5 filter and I have picked 32 filters, then output size is going to be 28 into 28 into 32. And now if I do this max pooling, okay, with max pooling, normally the size would have been 14 into 14 into 192, right? If I do this max pool, yes or no?
Yes, sir.
But assume that I have done padding and I have done same convolution, okay? Then of course I can have 28 into 28, yes or no? Right?
Yes.
But what should be the channel value? Channel value will be 192, right? Yes or no?
Yes, sir.
So for the time being, you'll see that here they have chosen, instead of 192, what they have taken? They have taken what? 32, right? So how they have taken 32, I will talk about that later. But for the time being, let's assume that after doing this max pooling, the output is 28 into 28 into 32. So if I combine all these outputs and if I concatenate them all together, then what will be the size? The size will be 64 plus 122, 28, 32 plus 32. So you'll have an combined output of 28 into 28 into 256. And this one will go as input to the next layer. Is this understood?
Yes, sir.
Okay, fine. So let's move on. Now the question is that if I look at this particular one, okay, why can I not remove it? The question is that if I want to remove, okay, I cannot do this. I cannot remove this one. Let me see. Minute and Can you see my screen?
Yes, sir.
Okay. So what I was talking about is basically, so if I want to see that, okay, since I have to do a lot of convolution, I have to do 1 by 1 convolution, I have to do a 3 by 3 convolution, 5 by 5, maybe you want to do a 7 by 7 convolution. But let's look at, if I want to do a 5 by 5 convolution, let's see how many computations I have to do. Let's say for this particular single output in the output matrix, how many calculations or how many product-wise element-wise multiplication do you have to do? Can someone tell me? For this single
5 into 5 into 192.
yes, 5 into 5 into 1 net, because we know that this output will come from the convolution from a single filter. And what's the size of your filter? It is 5 into 5 into 192. That means this many, what do you have to do? Product-wise multiplication you have to do, and also addition you have to do. Fine. This is for a single output position. But in this output matrix, how many output values do you need to compute? You have to compute 28 into 28 into 32. This many. And if you see how many in together, you'll see that this is something around or more about like 120 million product-wise, element-wise product you have to compute. Also, you have to do the summation, right? So it's very large, right? The number of calculation is very large. Yes or no?
Yes, sir.
Okay, fine. So that means, and if you want to do it for 7 by 7 again, and if you want to do it for 3 by 3 again, you can see only to compute this block of data, okay, how much calculation you have to do. You have to, it will go towards like 500 million. Okay. So what we'll do, we'll try to make use of this 1 by 1 convolution, because the main hurdle comes from having a lot of channel information. For example, in this particular block, if I have 28 into 28 into 192 data, and if I want to do this 5 by 5 convolution with 32 different filters, okay, we have seen that I need 128 million operations to do over there. How about if I do a 1 by 1 filtering with 16 different filters, okay? Or that means filters means this, I want to do this convolution. What will be the output size? Doing this 1 by 1 convolution, what will be the output size? It's going to be 28, 28 to 16, right? Yes or no?
Yes, sir.
Fine. Once it is 16, then you can see that the size is same, because I have done this 1 by 1 convolution, but the number of channels has been reduced to 16. That means we have reduced the depth information. We have reduced it. And then if I do this 5 by 5 convolution with 32 different filters, what will the output size? The output size is 28 into 28 into 32. That means the number is same, whatever we have expected before, right? It was 28 into 32. Now the thing is that if I want to do this convolution operation, how many element-wise multiplication will you do and summation? First of all, the filter size is 1 into 1 into 192, and then you have to do it for this many outputs. So this is the number of calculation for doing this convolution. Now, if I want to do this particular convolution, how many calculations do I need? I have to have the filter size is 5 into 5 into 32. Sorry, not 32. Sorry. Filter size is what? 16, right? And this calculation has to be done for how many output positions? 28 into 28 into 2. This many, right? And if I want to see that through this step, how many calculations do I need in total? I can just simply add them together, and this becomes something like maybe 20.8, something like 12.8 million. So now you can see that if I have done this 5 by 5 filtering directly, but if I do this indirect filtering with this 1 by 1 convolution in the middle, how much computational save have we got? How much calculations
10
have you
times.
saved? 10 times, right? You have saved the computation almost 10 times, right? But whatever the output you're expecting, the size is almost the same. I mean, the size is exactly the same, right? Yes or no?
Yes, sir.
Okay. But you'll see that by selecting the appropriate number of filters, like here 16, okay, or maybe it could have been like 26, or maybe like 34, or let's say 64, something like this. By appropriately choosing the number of 1 by 1 convolution filter, you see that by directly doing this convolution, and having this indirect convolution may end up similar kind of performance results. Okay. Of course, you will not exactly the same, but you expect them to become as close as possible, right? Yes or no? But the benefit is that okay, you have to do some sacrifice with your accuracy, with your performance. But in terms of calculation, you have saved a lot of computational computations, right? Yes or no?
Yes.
Okay. So this is basically the motivation behind inception neural network. That means basically what I will try to do, I will try to have, like as you have seen here, I want to do different kind of convolution starting with 1 by 1, 3 by 3, 5 by 5, 7 by 7. But what I will do, instead of doing direct convolution, I will have an optimized, you can think in this way, I will have an optimized way of doing this convolution. Okay. So like as we have seen before, we have this input data matrix size of let's say 28 into 20 to 92. Then I can do this one by one convolution. I have taken 64 different filters. So the output size would have been 28 into 64, like you have seen over here, right? Yes or no? And then what I have done one by one convolution before doing this 3 by 3 convolution. And how many filters have I picked? I have picked 96, right? So, and if I look at the input channel, what was the input channel? It was 92. So did I do this volume reduction over here? Yes or no? So now since we have done this volume reduction, and then on this I will do this 3 by 3 convolution, and I have picked 128 different filters. So my output will become 28 into 28 into 128. And since we have used this intermediate 1D convolution, what will happen? Your computation will be significantly less. The similar thing we'll do for this 5 by 5 filter. We'll use this volume reduction or depth reduction. Okay, what we'll do? We'll use 16 different filters of 1 into 1 into 192, and your volume or channel or depth will reduce from 192 to 16. And then on this output, if we do this 5 by 5 convolution, we'll end up at 28 into 28 into 32. Fine. How about if we do this max pooling? Like we have used this 3 by 3 stride one, same convolution, max convolution actually. So what will happen? What will be the output size? The output size, as I mentioned before, is going to be 28 into 28 into 192. And after doing this max pooling, since we could not reduce the number of channels, then we can reduce the number of channels by doing a 1 by 1 convolution with 32 filters. So if I do 32 filters with 1 by 1 convolution, we know that the depth will reduce from 192 to what? To 32? Yes or no?
Yes, sir.
And if you compare here, though it is not showing a 1 by 1 convolution over there, but we now know that if I do this 1 by 1 convolution, this max pool channel number will reduce from 192 to what? To 32. Now understand that how they have got 32, right? Yes? Okay. So since we have done this, so basically what we have done at the end, we have got all those outputs and then we concatenate them. And then finally we have got the outputs of 1 by 1 convolution, 3 by 3 convolution, 5 by 5 convolution, and max pooling. And then we can, during this training phase, we can allow the neural network to find the correct filter size or the correct layer type, like whether it should be a convolution layer or whether it should be a max pool layer, and so on. So considering this convolution inception module, okay, so if you think that this is one inception module, by combining different inception modules, we can have different kind of inception network. And the design that you are looking over here is basically the inception network, which is popularly known as Google Net. Okay, it was basically proposed by Sejeti and others who were working at the time in Google. And according to that company name, they have named it Google Net. Okay, and it was also the winner of this ImageNet competition, ImageNet's large scale computer vision challenge 2014. It was the one of the winners actually. It has 9 inception models. So how do we have 9? So if you look carefully over here, so do we see that inception module that you have seen here? Yes or no? That means you have your input, you do the 1 by 1 convolution, okay, then you have this 1 by 1 convolution there, 1x1 convolution there, and then here you have this max pool, you have this 1x1 convolution, and then here what we have, here we have this 3x3 convolution, here we have this 5x5 convolution. That means you see an inception module here. Now how many inception modules do we see here? Now here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can see 9 inception modules. So this is basically the inception network that we see in GoogleNet. Understood? But then you can see that there is some slight differences. For example, here you can see that there is the output, and then we have this 1x1 convolution followed by this concatenation. Okay, but if you look at this particular inception module, you can see that this input after this activation, what do we have? You have added an extra max pooling layer. Can you see it? Yes or no?
Yes.
I mean, there is a small variation. That means sometimes you'll see some extra max pooling. You will see over here, like here you will see there are some extra max pooling added. But apart from that, you'll see that they have used these 9 similar kind of convolution modules. And then finally, what they have done, they have got their output, and they have done this max pooling. There's fully connection layers, dense layers, and then they have done this softmax, and then finally they have got their decision. Okay. So that means after going through 9 layers of convolution inception layers, they have found the decision. But you'll also see that they have defined some branches where they wanted to see some intermediate decisions from this after 1, 2, 3 inception layers. They wanted to see what kind of decisions do I get over here. Similarly, they have, I mean, 1, 2, 3, 4, 5, 6, 7. After 7, they again, or not 7, after 6, they again wanted to see, I mean, what's the intermediate decision if I had taken 6 inception modules, okay? And then finally, after 9, they have got their final decision, okay? So basically, during this iteration, okay, during this learning, they also try to see whether few layers or more layers is ResNet, okay, digital network, and people might be using this VGG16. Even nowadays, you'll see that people are using a modified version of VGG16, okay, and there are some other improved version of VGG16 too. Inception network was once very popular, okay, it was once very popular, but nowadays it has been, I mean, overcome by other popular networks. Okay, so up to this, do you have any questions? No?
Sir,
Okay.
in GoogleNet, can you go to the Google slide?
Okay, this
Uh,
one.
Sir, the backpropagation, the loss function, are we calculating from the uh, rightmost output or the intermediate decision boundary decisions?
So basically, the thing is that we are always going to compute. Normally, what we do, we are always going to compute from the last layer, right? Yes or no?
Yes, sir.
But if you want to see the intermediate decision throughout your what can I say, during this back propagation, right? You always go back propagation then forward pass, back propagation then forward pass, right? Yes or no? Then we want to see that during this intermediate step, what kind of output or what kind of decisions we could have got if we have less and less number of layers. Okay, so basically it's the final loss function that basically mostly influence in computing the loss and propagate the loss behind.
Okay.
So I haven't talked about all the nitty-gritty of these neural networks actually. So that's why I have given you the papers. I have given the name of the papers, also the link of the papers. If you click over there, you can find the details and all the input insights, okay, inside behind their motivation. Okay.
Okay.
Any further questions?
No, sir.
Okay. Okay, since we have end today's lecture, okay, let me where is your attendance link? Okay, did you get the link to your attendance?
Yes, sir.
Okay. So please give your attendance.